Most people walk past the ground that holds gold because it doesn't look valuable. It looks broken. It looks rusted. It looks like the kind of place nothing important could ever come from. The colors are dull reds, browns, and yellows. The rocks crumble easily in your hand. Surfaces appear eaten away, almost diseased. To an untrained eye, this is wasted ground. But to someone who understands geology, this is often the exact opposite. This is what the aftermath of a powerful mineral system looks like once time has had millions of years to work on it. Gold does not form in peaceful environments. It forms in systems driven by heat, pressure, chemical fluids, and structural stress deep within the earth. Long before erosion exposes anything at the surface, those systems move through fractures in rock, carrying dissolved minerals. Those fluids are aggressive. They change the rocks they pass through. They add minerals, remove others, weaken structures, and leave behind chemical signatures that remain long after the original process has stopped. What you see today at the surface is not the event itself, but the weathered remains of that event. When mineral-rich fluids rise through cracks, they don't just deposit gold, they alter everything around them. Iron-bearing minerals, sulfides, and reactive elements are introduced into the host rock. At depth, these minerals are stable. But once uplift and erosion bring them closer to the surface, they begin to react with oxygen and water. This is where the transformation begins. Iron oxidizes, sulfides break down. Chemical bonds that formed under extreme conditions start to fail under atmospheric exposure. The rock literally begins to rot. That rotting process is what creates the rusty colors so many people ignore. Reds, oranges, ochres, and deep browns are not random stains. They are oxidation products, evidence that iron-rich minerals once existed there in abundance. Those iron minerals are extremely common companions to gold-forming systems because both are transported by the same hydrothermal fluids. The gold often remains chemically unchanged while its surrounding partners decompose. Over time, the supporting minerals disappear, leaving behind altered, weakened material and, in some cases, liberated gold. This is why highly mineralized ground often looks structurally poor. It may appear fractured, soft, or shattered compared to surrounding rock. That weakness is not accidental. It reflects the intense chemical replacement that happened when mineralizing fluids moved through the area. Strong rock was turned into something else. Original minerals were dissolved and replaced. New minerals grew in their place. Later, weathering attacked those replacements. What you see now is a rock that has lived multiple lives. Many of the world's important gold districts are associated with what geologists call alteration zones. These zones rarely sparkle. They rarely look dramatic. Instead, they look bleached, stained, or decomposed. The textures may resemble clay, chalk, or crumbly sandstone, even if the original rock was once hard and crystalline. This transformation is one of the clearest surface expressions that intense chemistry once occurred below. Gold survives this transformation because it is chemically resistant. Unlike iron, copper, or sulfur-bearing minerals, gold does not oxidize easily. It does not dissolve under normal surface conditions. While surrounding minerals rust away, gold remains intact. Over immense spans of time, this creates a strange contrast. The valuable material persists while the environment that carried it collapses into something that appears worthless. Another reason these environments look unappealing is that repeated fluid movement tends to destroy visual uniformity. Instead of clean layers or solid formations, the rock becomes mottled, veined, patchy, and inconsistent. These irregular textures record multiple pulses of fluid activity. Each pulse may have introduced slightly different chemistry, overprinting earlier stages. The result is visual chaos, but geological significance. Weathering then exaggerates that chaos. Water seeps into fractures created by earlier alteration. Freeze-thaw cycles expand cracks. Oxidation travels deeper. Entire sections may break down into loose material called saprolite, a deeply weathered rock that still preserves original structures but feels soft enough to dig with simple tools. To someone expecting solid bedrock to host gold, this material seems like the wrong place to look. Yet it can represent the exposed top of a once active mineral system. Color variations across a hillside can also reveal this hidden history. Instead of uniform tones, altered ground often shows gradients, transitions, and irregular patches. These are not random. They can reflect differences in fluid pathways, permeability, or mineral concentration during formation. Each color shift represents a slightly different chemical outcome from the same overarching process. Importantly, these visual signals are stable across time. Seasonal change may affect vegetation or moisture, but oxidation patterns remain. Once sulfide minerals break down and iron oxides form, those colors persist for thousands or millions of years unless physically eroded away. That permanence makes them reliable markers of past mineralization. People often imagine that valuable geology must look dramatic, sharp, or crystalline. In reality, the most telling signs are frequently subdued. Systems rich in chemical history tend to erase their own original beauty. They exchange it for evidence of transformation. The ground becomes a record of reactions rather than formations. Even quartz, commonly associated with gold, may appear dull or heavily stained in these settings. Instead of clean white veins, it can be fractured, iron-marked, or partially dissolved. This again reflects exposure and weathering rather than absence of mineralization. The quartz formed deep underground, but its present appearance reflects everything that happened afterward. Understanding this sequence changes how ground is evaluated. Rather than asking whether a place looks rich, the better question is whether it looks chemically worked over. Evidence of breakdown can be more meaningful than evidence of preservation. A location that appears untouched may never have hosted the processes necessary to concentrate metals at all. Over geological time, landscapes are sculpted not just by erosion, but by exposure of deeper environments. Mountains rise, rocks fracture, and once buried systems are slowly revealed. By the time they reach the surface, they have already endured transformation, uplift, and weathering. Expecting them to appear pristine ignores that entire journey. The irony is that gold is often easiest to access where the surrounding rock has suffered the most alteration. The weakening of host material allows erosion to remove what once concealed the system. As softer altered zones wear down, resistant materials and any liberated gold can accumulate nearby. The destruction of one set of minerals becomes the pathway to discovering another. This is why experienced observers pay attention to subtle disorder. They notice where rock loses cohesion, where staining concentrates, where textures change abruptly without obvious structural explanation. These are surface expressions of ancient movement, chemistry, and pressure interacting over immense time. In these environments, ugliness is not a flaw. It is evidence. The ground is not simply weathered, It is weathered after having been fundamentally changed at depth. Every rust tone, every softened edge, every fractured surface can be part of a story that began far below and long before the present landscape existed. Recognizing that story requires shifting expectations. Gold-bearing systems rarely advertise themselves with brilliance. Instead, they appear as remnants of something that has already happened, something powerful enough to alter rock chemistry on a large scale, but distant enough in time to be masked by decay. When viewed through that lens, rusty soil is no longer just oxidized dirt. It is the exposed chemistry of an ancient hydrothermal engine. Crumbling rock is no longer weak ground. It is altered material that has endured multiple stages of transformation. What appears unattractive may represent the most meaningful signal left behind. Gold does not need to shine to announce its presence. The environment around it does that in quieter ways, through persistence of color, texture, and breakdown patterns that remain long after the original mineralizing event has ended. In the quietest corners of American wilderness, far from paved roads and phone signals, there exists a geological pattern so consistent that geologists almost treat it as a coded message from the earth itself. A message written in stone, whispered through time, and understood only by those who know how to read the land. They call it the three-rock combination, a natural lineup of minerals and textures so tightly connected to gold that whenever these three appear together, the likelihood of gold rises from possibility to near certainty. Most people walk through valleys and stream beds without noticing the clues lying at their feet. But gold is never random. It never scatters without logic, and it never travels alone. It forms, moves, and settles according to precise geological laws. Laws that leave unmistakable signatures behind. These signatures aren't obvious. They don't shine, they don't sparkle, and they don't call attention to themselves. But geologists have learned to recognize them as the silent fingerprints of ancient gold movement. And today, you will learn to recognize them too. Gold begins deep underground, born from mineral-rich fluids rising from molten rock far beneath the crust. As pressure builds and temperatures soar, microscopic particles of gold dissolve into superheated water, drifting upward through cracks, fractures, and faults. And as the planet cools those fluids, gold begins to precipitate out, sticking to the edges of the fractures, coating quartz veins, pooling inside breaks in the bedrock. This entire process leaves behind companions, rocks and minerals that form under the exact same conditions. When you understand these companions, you understand the entire Golden Trail. The first of these geological companions is a type of metamorphic rock that looks as though it has been pressed, heated, and folded by the weight of the continents themselves. Smooth, shiny, layered, and often glittering with mica, this rock records ancient heat and pressure stronger than nearly anything on the surface today. Geologists rely on it because this type of rock forms in the exact environment where gold-bearing fluids originate. It is schist, one of the most respected host rocks in American gold geology. Whenever you step into a region where schist appears, especially in mountain belts stretching from the Appalachians to the Rockies, you stand inside a zone shaped by the very same forces that produce gold. But schist alone isn't the signal. Gold needs a highway, something that carried the fluids upward and froze them in place. And for millions of years, that highway has been quartz. Thick white or translucent quartz veins cut through darker rock like frozen lightning. They slice across schist, granite, basalt, and almost anything in their path. When hydrothermal fluids carrying gold cooled inside these veins, they left behind crystals, fractures, iron staining, and sometimes visible flakes of precious metal frozen in time. Even the rusty orange-red stains that coat quartz in gold country tell a story. They signal iron oxidation, nature's way of marking the path of mineralization. Where quartz cuts through schist, the story of gold becomes clearer. But the real confirmation appears in a third rock, an often overlooked heavy, rusty, metallic stone that forms at the surface when iron-rich minerals weather. It can appear deep brown, jet black, or blood red, and it leaves stains on anything it touches. This stone is ironstone, the unmistakable marker of a hydrothermal system that once pulsed with mineral-rich fluids. Gossan caps, iron crusts, limonite masses, and hematite-laced stones are nature's final stamp of approval. They say, yes, the chemistry, the temperature, and the fluids that create gold were here. When schist provides the birthplace, quartz provides the pathway, and ironstone reveals the chemical transformation. The three-rock combination is complete, not a myth, not a rumor. A geological pattern repeated across the United States wherever gold has been historically and scientifically confirmed. From the Sierra Nevada range to the Georgia Gold Belt, from Arizona's iron-rich ridges to Colorado's metamorphic cores, from the river-cut canyons of Oregon to the ancient schist belts of Alaska, this trio appears with remarkable consistency. Finding these three rocks is like reading a coded map. First, you notice the schist, layered, glittery, easily split, shaped by immense heat. You run your hand across its surface and feel the grain of an ancient world. Then you notice the quartz, bright white, jagged, cutting across a darker rock like veins of frozen sunlight. And finally the ironstone, heavy, metallic, oxidized, a deep, rusty color that stands out even in the shade. These rocks are not random. Their presence together is a geological conversation, and each stone adds a layer of meaning. Gold hunters, prospectors, and professional geologists use this combination in the field without fanfare. They know that if schist and quartz appear together, the ground has history. But when ironstone joins the scene, the ground has potential. And when all three appear within walking distance, sometimes even within arm's reach, you have stepped into a zone where gold once moved, gathered, and concentrated. This is the exact method used in American exploration. Locating metamorphic host rocks, tracing the quartz veins that fracture them, and studying the oxidized ironstone that reveals the age of the system. Companies invest millions in drilling programs based on this geological triangle. Prospectors stake claims on ridges where these rocks intersect. And ordinary people, those who understand these quiet clues, find gold in places others overlook. When you walk into a landscape with these three rocks, you begin to see the world differently. Hills that once looked ordinary now appear as chapters in an ancient story. River bends become pathways that once carried broken quartz downhill. Rust-colored ridges become signposts pointing toward old veins. Even the gravel beneath your feet becomes a record of erosion, carrying fragments of the very rocks connected to gold. The power of the three-rock combination is not just scientific, it is practical. It tells you where to look, how to interpret the land, and where gold is most likely to be trapped today. It teaches you that gold does not scatter randomly, but follows rock types, structures, and chemistry. And once you understand those patterns, you can predict where gold should be, even in places you've never explored before. Whenever you find yourself in a canyon, along a creek, or on a lonely mountainside in the American West or East, And you notice these rocks around you, schist whispering of deep origins, quartz marking the pathways of ancient fluids, and ironstone confirming the mineralizing conditions. Stop for a moment. Look around. Listen to the silence. Because you may be standing on the threshold of an area where nature once hid gold with deliberate precision, and the landscape around you is quietly waiting for someone observant enough to interpret it. The truth is that gold rarely reveals itself easily, but it leaves unmistakable hints in the rocks that accompany it. When you know how to read these hints, the wilderness becomes a geological map rather than a mystery. And this second part of the story begins with understanding what happens next, how to follow these rocks, how to interpret their placement, and how to transform geological clues into real discovery. Once you identify schist, quartz, and ironstone in the same environment, the next step is to determine how these rocks relate to each other. Geologists are trained to look for alignment, orientation, and the way veins intersect the host rock. When quartz veins cut across schist in clean, sharp lines, it means those veins likely formed during a period of intense hydrothermal activity. And hydrothermal activity is the engine of gold formation. These veins can run uphill, downhill, or across a slope, but they usually align with old fault structures, cracks in the earth that once served as pathways for mineral-rich fluids. By following the direction of the vein, you essentially trace the path that gold-bearing fluids once traveled. Ironstone plays an even more important role at this stage. Its presence does not just confirm mineralization, it reveals the age and exposure of the system. Ironstone typically forms when sulfide minerals weather and oxidize at the surface, which means the area you're standing in has undergone long periods of erosion. When these oxidized caps sit above quartz veins, they often point toward deeper, unweathered sections where gold can remain locked inside the rock. This is why some of America's richest gold finds have been made just beneath iron-rich hilltops. The rusty color is not just a stain, it is a sign of ancient chemical transformation. As you walk along slopes or creek beds in the United States, you may notice that these rocks appear in clusters. This clustering is not accidental. Water, gravity, and erosion naturally concentrate the fragments of these rocks together, especially near old volcanic belts and metamorphic terrains. When all three appear in creek gravels, it often means the original source is nearby, uphill or upstream. This is one of the most important clues prospectors use. Rocks always travel downhill, and gold, being heavier than nearly everything around it, tends to settle in predictable traps. So if you find these rocks together in a waterway, the next step is to trace their origin. Tracing uphill from a creek, following the fragments of schist and quartz, often leads you to the bedrock exposures where the original veins remain frozen in place. Along the way, ironstone scattered across slopes confirms that the ground has undergone oxidation and mineralization. Every rusty fragment you touch is part of a chain of evidence stretching back millions of years. And as the rocks become larger, more angular, and more freshly broken, you know you're getting closer to the source. American geologists often refer to this approach as reading the land, because the terrain itself is the text. The shape of the valley, the tilt of the hillside, the position of old boulder fields, all carry meaning. Gold-bearing areas frequently appear where steep slopes flatten, where ridges intersect like braided threads, or where old river channels changed direction long ago. If the three-rock combination appears in these zones, the probability of gold increases dramatically. Many of the best modern gold discoveries in the United States weren't found by accident. They were found by people who understood how to interpret rock combinations, and follow them back to their origins. And it is here where the process becomes almost meditative. You take your time, you slow your steps. You observe the ground with calm curiosity. The wilderness becomes a quiet teacher. Small details begin to stand out. The sound of crunching iron-rich gravel under your boots. The distinct shimmer of mica from schist in the afternoon sun. The glint of white quartz between broken stones. You begin to sense a pattern. The environment feels mineralized, as if the land itself still remembers the ancient pressure, heat, and geological violence that once shaped it. When you reach the source area, whether it's a ridge, a hillside, or a bedrock exposure, you'll often notice the rocks aligning in a way that tells a story. Quartz veins may widen, ironstone patches may intensify, and schist layers may twist and fold in dramatic patterns. Sometimes you find broken quartz scattered downhill from a vein exposed high above. Other times you see rusty staining on the face of a rock wall, indicating that sulfide minerals once lurked inside. If you examine these surfaces closely, you may notice tiny fractures where gold once moved. Even if the gold is not visible, the structure of the rock carries the memory of mineralizing fluids. And this brings us to one of the most powerful techniques geologists use: examining contact zones. A contact zone is where two different rock types meet, such as the boundary between schist and quartz. These boundaries are prime locations for gold deposition because the change in chemistry and pressure often cause gold to drop out of solution. When quartz veins cut through schist and ironstone coats the edges of those veins, the chances of gold increase significantly. Many American gold mines began at these exact boundaries, but gold is rarely found at the surface. It is usually locked inside the quartz veins, trapped in fissures, resting in cracks in the bedrock, or broken off and carried into nearby waterways. This is why panning in areas with the three rock combination is so effective. If gold has eroded from the veins, it will settle into natural traps, behind large stones, inside cracks in the bedrock, beneath dense gravel layers, and in places where fast water suddenly slows down. These traps exist everywhere from Alaskan streams to Appalachian rivers. And because gold is so heavy, once it settles, it tends to stay put until major floods move it again.